Good morning, everyone. Allow me to introduce myself. I'm Reed Hinkle. I'm Senior Manager for Embedded Security Market Development for ARM. I'm actually presenting on behalf of a colleague, Suresh Marisetty, who had a family emergency, so he was unable to attend. So this presentation is something that he's been working on for quite some time. If you have any questions at the end, I'll do my best to answer them. And if I'm unable to, then I can refer you to Suresh. So this morning, I would talk a little bit about the landscape of what we're facing in terms of security, the problem statement, or what we're actually facing as an industry and as an ecosystem, establish what we mean by root of trust and how that's changed in the last several months, a little bit about the root of trust models, and then talk about beyond the root of trust what's required in terms of security for IoT. So we have connected devices everywhere. I think we're all well over 1 billion on our way to hundreds of billions or even trillions of devices once we really start deploying these devices in this sort of scale that we all believe will happen over the next 15 to 20 years. I think the important thing to note is that the requirements for an array of these devices are span the gamut. Everything from things that are going to require very low levels of security to things that are actually quite high. So as an industry, we have a lot of experience, and as ARM, we have a lot of experience with payment grade, security authentication for DRM and things like that. And in the last 12 months, since we introduced the Cortex-M family, we're actually bringing a similar level of hardware functionality to the microcontroller. And so now we're able to address hardware security at a much broader array of devices. So the problem statement is that we have to basically secure our devices against malicious attacks, the remote malicious attacks. And so we look at basically the 3 fundamental elements of security, or some people call it CIA. We don't want to think about it in terms of the Central Intelligence Agency, but here, confidentiality, integrity, and availability. So you want to make sure that your secure secrets are confidential. The device has integrity to fend off basic compromise from those secure pieces of data, whether they be keys or certificates or sensitive data, and availability to make sure that your device is available at all times so that it can be updated, or at least in devices that might sleep, that whenever it is available, that you're able to manage, maintain, and preserve the robustness of that device. So talk about the threat focus. So we effectively have four different areas where we see attacks: the communication attacks, physical attacks, software attacks, and lifecycle attacks. And we basically have 4 fundamental areas that we concentrate and deploy against those attacks. That includes the encryption, the secure device management, hardware and reinforcement, which is an area that ARM focuses on very significantly in its architecture, and then the physical attacks, so the anti-tampering capability that we need to build into our devices. For IoT devices, we have as I mentioned, basically we see that the communication attacks are a given. We need to protect against those sorts of attacks. The software attacks are on the rise. Lifecycle attacks are very much a very important issue in terms of being able to do safe, secure, and robust software updates to your system. And to a lesser degree, the physical attacks in IoT are on the rise, but because the attackers are actually getting better tools, it is an area that we need to, and I would say also not just better tools, but at a lower cost. So we have to raise the bar in terms of the physical attack posture as well. So talk a little bit about the generic security requirements. If you look across the various different markets that we're all focused on in the industry, automotive, healthcare, industrial, wearables, and the home, what you'll find is there's several of the security requirements that are listed here that are actually quite common across all these various different end equipment markets or market segments. And so from ARM's perspective, our aim is to make sure that we cover the baseline of all these more or less at a building block level that's baseline given the class of device that we're enabling our silicon providers to build and then for their customers to build in a final device. Obviously, there's additional requirements that are more market specific, and so those have to be accounted for as well. But we wanted to make sure that in our baseline architecture, we address the common core. When we talk about the initial root of trust and the chain of trust, really at the heart of that are the keys. And so basically, that's where you need to have the most security for that base level. And then from the aspect of radiating out from that, you're looking at ensuring and securing at each ring, and that basically means that you have least privilege as you move out towards getting out to the trusted libraries and the RTOS where you have most privilege to be able to do things. And so building your architecture so that you protect each ring, you have an increasing level of protection at each ring. So the basic security requirements of the system are basically preserving that root of trust or preserving the keys and certificates in your system, and then making sure that you have boot code that can't be compromised. And so that basically, from our perspective, means the initial boot block has to be immutable code. It can't be anything that can be modified. So it has to be secured in a walled garden and unmodifiable in the system. So that means we have to take care to make sure that it's very robust. And then on top of that, we can build the other levels of security. The execution environment needs to be fully contained. And we'll talk a little, as we get through in a few more slides, talk about the different level of containment that from an architecture perspective that we can build. So the crux of the problem is one size doesn't fit all. As we mentioned, you have an array of devices, a sensor that actually is a very simple sensor. Of course, you want to make sure it has a certain level of security, but it doesn't need the same level of security as like a payment terminal or a gateway, for example. So that's really the crux of the problem that we face in terms of being able to make sure that we can deploy security at cost levels that are acceptable to the market. So from a secure boot flow perspective, the chain of trust starts with the initial boot block, and then basically each level of code above that is loaded, and it's basically secured at each level, typically by a security certificate. So it's basically signing your code and then verifying that code as it gets loaded. So the baseline boot secures the firmware boot, which secures the OS code, which secures the application code that's loaded in the system. So if we think about how we've deployed security in the past on systems where you have a CPU and external memory and multiple different peripherals externally, the industry got together through the trusted computing, the TCG Trusted Computing Group, and developed a TPM standard. And so that was basically a way to actually create a secure root of trust in an external device. What we're really addressing at ARM in our architecture is how do we actually move what was in an external device internal to the chip or the main SoC in your system, which may be an applications processor that you're space constrained on your board and you don't want to have external devices for security or microcontrollers where you have even more space constraints and even power constraints in your system. But to understand exactly how it works, I think, or what we're trying to do, we're trying to move a lot of the similar functionality that a TPM serves today internal to the chip, or the SoC that our silicon partners build. So what that really mandates is that you have secure storage and platform integrity reporting, so that you can actually query the chip to make sure that you know that the chip has gone through the stages properly and that it's properly configured. It can tell you, that each stage of the boot's been properly performed, and then that gives you your platform authentication. I skipped over, where it's being used. It's actually being used extensively in clamshell laptop PCs. It actually became a requirement a little over a year ago by Microsoft for all Windows 10 platforms have to have TPM functionality built into their platform. We're seeing it required, it's been a requirement in servers for even longer than that. And then we're seeing the Industrial Internet Consortium actually add TPM functional requirements to industrial gateway systems. So we're seeing and we'll talk a little bit more about the function that it provides in a moment, but you'll see that a lot of the same principles go across all these different devices, established in the secure root of trust as each stage of the software is launched. So talk a little bit about measured boot, so software integrity management. So from a flow perspective, the chain of trust starts with that initial boot block. So that initial boot block brings up the system, and then it actually starts working with the TPM to actually do what's called integrity measurement. So that's actually taking the image and the signature, computing the measurement of the inbound software or the software that's going to be loaded against what the certificate says that the signature should be of the software. And if it's a match, then it moves to the next level of boot in the system. So in a PC system, it would be your baseline chip, basically booting up, and then in preparing itself for the BIOS or the UEFI, and then after that, after it verifies that boot, then it will move up to the operating system boot, and then certain applications then are loaded on top of that. A popular application in PCs, or one of the core ones that's used, particularly in commercial business, is BitLocker, for example. So it's basically securing the disk drive or the disk image in your system to make sure that it's robust against malware and attackers. So a little bit about secure boot versus measured boot. They assure the same end goal, but secure boot is really at the SoC level. It's what actually brings the initial root of trust environment into being, and then that's combined with the TPM to create the measured boot environment. From a models perspective, we have, as we mentioned, wide variety of applications out there, and then we have constrained applications. So you have everything from smart locks to asset tracking to devices that are actually measuring different medical or biological factors, and then also medical nanorobots. So you have an array of those devices, and they each have different level of requirements from a security perspective. So from within the IoT device, there's a diverse functional set of endpoints, and it gives you a diverse set of security requirements that you have to account for in your product designs. So we talked a little bit about how things are accomplished externally. Now we need to move the discussion, and from ARM's architecture perspective, what we're doing is actually taking what used to happen external to device and then actually embedding that internal to device. So at the beginning you have the single processor environment, or the primary environment. So that's kind of the state of microcontrollers today, and many processors that don't have a TrustZone-like environment, or a TEE type environment. So there's no secure enclave or no security block inherent to the SoC, and there's also no hardware environment, hardware enforced sandboxing environment. So that moves up to the single processor environment, or primary environment with TrustZone. So you have the hardware enforcement, but you don't have a secure enclave type capability built into the chip. So from that perspective, that you can actually use that TrustZone to create what would be essentially a virtual secure enclave. But they're still sharing the same processor, so there's still a little bit of risk there. Then you move up to the non-TrustZone primary processor element, and then in a non-TrustZone environment. So that's common a lot in a lot of ARM's SoC or our silicon providers actually have built that secure environment with the as a non-TrustZone PE with a non-TrustZone secure element. So in other words, there's no TrustZone for the software on the secure element. Then you move on up the scale to the enhanced SE root of trust, in which case you have the non-TrustZone PE and the TrustZone SE. So it's actually a secure element protected in a TrustZone. And then that move on up the scale. So basically, when you start moving up the scale, you're moving into the areas where you can achieve the level of security that you need for the payment systems, where you need for medical devices, where you need for autonomous automotive devices. So obviously, at each level, you're adding a little bit of complexity and also a little bit of cost. So what's new with the TrustZone extended to the MCU-Family? So we increased the root of trust robustness. So the basic building blocks are the cryptography, the secure system, secure storage, and a true random number generator. Built on top of that is the trusted, that actually becomes part of the trusted hardware. So there may be additional hardware functionality built into the system, like there is on a V8M platform. And then on top of that is trusted software, or the firmware that operates the system. So then in terms of the ecosystem, we also have confidentiality of the silicon provider elements. So that would be trusted hardware that they may have added on or layered into the system. And on top of that would be additional firmware and trusted drivers for the system. Then you move on up to the confidentiality of third-party software IP. So we have a number of partners in the ecosystem who are basically adapting their software that traditionally ran in a classic non-secure platform environment, and they're moving that into the TrustZone environment. And then sandboxing, so basically creating the secure operation area for your trusted and your secure functions in your system. So foundationally, so basically we went to the no explicit root of trust. That's the very beginning. Build on top of that TrustZone, build on top of that secure enclave, and then that gives you the TrustZone with the primary element, and then the secure enclave, and then the secure enclave with TrustZone. So each level, an additional level of additional security robustness. So the security by separation element here is absolutely critical in terms of the malware attacks. Unless you have the ability to have the initial boot fully secure, and then be able to check each level of the software that's loaded into the system, you have a very difficult time knowing when you've actually avoided being rootkitted or having malware injected into your system. And there's additional software that can be loaded. So ELAM software is basically the ability to detect and reject any kind of malicious software that attackers might try to inject into the system. And so that defines the area where you actually secure your trusted and your secure functions, and it's sandboxed, or actually that's accomplished in hardware. And so you use that secure boot and loading of the secure trusted firmware to actually set up that environment and manage that environment over the life cycle of the product. So from an IoT offering perspective, the V8M series, there were our two members of the family today, the Cortex-M 33. I'm not going to go into a lot of detail because we have limited time. Wanted to make sure there's time for a few questions. But this is effectively equivalent in terms of the performance level, the sort of applications that would fit into a Cortex-3 or 4. It actually includes the secure partition management capability and additional functionality to actually attribute memory addresses and preserve those as secure, including not just the RAM or the flash, but also securing the memory spaces for any of the peripherals that you want to actually be classified as secure in your system. And then the Cortex-M 23, which is targeted at the ultra-low power applications. Its sort of targeted applications would be similar as you would target with a Cortex-M0 or M0 Plus. And so you'll see a couple of building blocks disappear from that, but the core functionality from a secure architecture point of view still applies. It just is extracting the functionality that would be available in an M33, and that's the only thing that's really not present in this platform. So from an SoC perspective, we talked a little bit about having the embeddable root of trust that's actually a secure enclave. And so that's really this first diagram here. So in this case, you actually have all the security elements, the boot ROM, secure RAM, the root of trust keys, the crypto, and the system mapping, all controlled within a separate secure processor. So it's a separate secure CPU. So that's what we mean by a secure enclave. So basically all of your system secure function and all the foundation of what actually runs from a secure or trusted function aspect happens inside of that secure processor. So it's completely isolated or firewalled from the rest of the system. Then what we just introduced with the V8M is basically the root of trust TrustZone. That's obviously something many of you that have been working on ARM Cortex-A platforms for some time are very familiar with TrustZone. And so what we've effectively done is taken a lot of the functionality that was done in software with a little bit of hardware enforcement, taking a lot of those principles and then applying those to microcontrollers. And we do it in hardware, so the context switching between the secure and non-secure world is incredibly fast. That's including the interrupts secure interrupts are handled at hardware speed. So from a summary point of view, or summary slide here, we have the hardware root of trust functional requirement is a functional requirement for any secure device. It's absolute necessity. And the more we can actually bring that hardware root of trust and additional trust functions inside the SoC, the more secure system that we can build, and we can actually do it at lower cost. Many endpoint connected devices exist with inherent constraints. I didn't neglected to mention, one of the chief among those in terms of IoT devices is really the constraint of power. We have a lot of sensors, remote sensors that either operate on power that they're able to attract from their environment, or very small batteries, and they're not always constantly running. So that also has to be accounted for in the security architecture. So they may wake up, communicate, and then go back to sleep. So you have to basically have a very effective way to cover the security in that sort of a use model. And TrustZone from ARM V8M provides a flexible rooted trust solution that can be deployed across a wide variety of those target applications. And so that we believe it provides the base building blocks across a number of end equipments, and then there can be additional security added on top of that by our silicon partners or by the device manufacturer themselves. So if there's any questions, be happy to try to field those. If they go beyond my depth, then I'll refer those to my colleague. Yes?
So you talked about the two-part grid, that some of the new people like Microsoft and Ethernet lines now demand TPM functionality.
Yes.
The problem is the TPM functionality is not part of or compatible with TrustZone global platform specs. So are you going to try to convince these groups that this is close enough for it to match requirements, or are you going to actually have to do exact TPM?
So they also offer a firmware version of TPM as part of the spec. Was the contribution that ARM had from the very early days of TCG. Most of the ecosystem accept that, or most of the OEMs accept that, to the degree that we can actually build additional protections or additional functionality that can serve and protect that TPM function in the system, that will bring in more trust as that being a solution that's acceptable to the market. For the most part, it is accepted, but at the same time, it's hard to get some system designers to trust a new system. So it's incumbent upon ARM to actually work with our partners to create the reference designs and the architectures, some of which, if you've attended any of the different sessions related to security, you're beginning to hear about some of those initiatives. And I would be looking, at ARM over the next several months to actually be introducing additional initiatives in the space. Other questions? Well, thank you for your time. If you have questions after the in between now and the next speaker, please feel free to come up, and I'll endeavor to answer them. Thank you very much.